Hello everybody, thanks for joining and welcome to How to Design for NanoSTAKE. We are going to be talking about NanoSTAKE as a technology and then how to design your plastic parts for it so that they can work really well. And of course, like always, we'll be answering your questions as we go along. Many of you have found the chat already. That's great. Please continue to use that and ask your questions as they come up. We don't want to save your questions for the end. We want to answer them as we are going along. So we will do our best to stay on top of the chat. And if you ask something that we're going to address, like in a few slides, we might say that. But for the most part, we will be answering the questions as we go along. So now, future airplane mechanics, soccer players, product designers, and excavator drivers, let's get started. Here's a quick overview of who Extol is. We solve complex plastic manufacturing challenges. And if you look at our logo, there's sort of a graph on the left-hand side. There are companies on one side that have plastic welding expertise, and then others that have custom automation expertise. What we found is that plastic welding providers don't do very well with custom solutions. Alternatively, custom machine builders lack plastic welding expertise, so it's hard for them to provide a robust solution. Extol is the best of both. We have both plastic welding expertise and custom automation expertise, and that allows you to get a configurable plastic welding solution that's optimized for performance. We break this out into three different areas: engineering services, plastic assembly technology, and custom automation. So we're looking to help customers with challenging applications, and usually that means we start very early on in your process. We provide engineering services that help you validate your design and do some development work on it, do prototyping, do all kinds of testing. We'll provide advice. We can give you 3D printed parts, lots of different ways that we can help you get your design to a point where you're confident it's going to be successful in production. And then, of course, plastic assembly technology. There's all these different technologies available today. Some of these are welding technologies where we're bonding two plastic materials together. And then others are staking technologies. And of course, today we're going to be talking about NanoSTAKE. Just a quick point out here, ultrasonic can be both welding and it can be both staking. But our topic for today is all about NanoSTAKE. So
we really try to be your easy button when you need to stick plastic to something, weld, stake. There's a lot of other technologies out there, but we have a wide breadth of products that we can offer. And so when you come to us with a problem or a potential solution to what you need to, stake or weld, we have a lot of different technologies that we do offer. And so we're not trying to pigeonhole our customers into, hey, stake everything, because that's what we sell. Mm-hmm. Just wanted to let everybody on the call know, we try to be your easy button, so to speak, when plastic welding or staking. All right, so as far as staking goes, obviously we're going to be focusing today on NanoSTAKE. And so some of those products that you may run into are hot punch, ultrasonics, hot air, our other staking technology that we have available, InfraStake, and then of course NanoSTAKE. So as far as those technologies, there's pros and cons to all of those. Some of those we'll get into a little more in detail pertaining to NanoSTAKE, but hot punch has been around forever. It's down and dirty. Things that like to stick to hot tools are problematic, like PBTs and things like that. Ultrasonic is fast, but if you have Class A or sensitive components, they can be problematic. Hot air, again, fairly fast. You get washout, potentially Class A issues. So with the other technologies out there, obviously we're a little bit biased. But as far as staking technologies go, InfraStake and NanoSTAKE are really the Cadillacs in the industry, and we'll be focusing on nano and why that is. So just wanted to go over the NanoSTAKE process. So we'll be breaking this down. First stage is heating. So this is conductive heat stake technology. So we do have a heater core in the base of the module. We have an integrated punch. So if you are familiar with InfraStake at all, that is not integrated into the module. That's a separate component within the system. With NanoSTAKE, that is built right in. So first step, we come down to the boss height, starting height. We turn on the heat source. We then form to its final position. We drive cooling air through the cooling vents surrounding the base of the module, and then we retract and start the process over. So really, as far as what we're doing here, that's a little bit different. If you are familiar with InfraStake, instead of using IR, we are using truly conductive heating technology. So we're going to show you a couple videos, and then we can talk about each one in between.
Okay, so the first one here, the Smart Respond localized heating. This is a brand new video that we just produced yesterday. And we'll play it a couple times because it goes quick.
So before we replay that, what you just saw was a thermal camera, imaging camera that was stationed while we were staking. And what you can see is that the heating is very localized. It's very precise, and it's rapid heat, rapid cool. So as soon as we retract the module from the part, we're already cool, and there's a little bit of residual heat built up into the part, but the module itself is cool to the touch, so there's no burn hazards.
So let's do that again. You can see, I'm going to pause it. So you can see like the light, the bright spots in there. I think you can see my mouse. These bright spots are that's the actual heater inside of the module, and you're seeing that heat through the cooling vents, but just the tip of that module is hot. Everything above this area is all still cool.
Yeah. So then that's where the cooling air is kicked on, everything cools back down, retracts, there's a little bit of residual heat built up into the system.
Okay, so this next one here, safe for electronics.
You can see we're very close to some sensitive components there. This technology is really been great for PCB manufacturing and staking. So we don't have to really worry about surrounding areas. We don't have to worry about desolder like with hot air cold stake, vibratory type staking, ultrasonics. You can really start to disrupt those safe, those sensitive components. So with our technology, you can see we're very close. We're touching the PCB, and we're not disrupting any of that.
And then lastly here, multi-point automation. Minimum diameter possible for a 3 millimeter plastic pin.
Yeah, so as far as minimums, I would say there really isn't one. We've done very, very small staking components for, I think the smallest one we have staked is for a hearing aid application, and I believe that one was roughly a 0.5 millimeter in diameter. So we can do very, very small. We do have some limitations as far as max, but I would say minimum as small as you can really dream up. So
yeah. At some point, it becomes so small. I mean, if a stake point was the diameter of a hair, it's not going to provide any strength. The other question here is about how do printed parts handle the process. Very astute of you, Rob. That is a 3D printed sample there in the center, and it works great. So that particular one, I believe, was a polypropylene, and it was printed with HP multi-jet fusion. What else have we staked? Do you know with NanoSTAKE that's 3D printed?
We've staked our nylon.
Okay, so PA12.
Yep. I mean, really, we'll get to that slide a little bit later on, but basically if it's melt processable, so most of these 3D printed materials are in fact melt processable. If they weren't, they couldn't print them.
Mm-hmm.
So I would say really any of those products that are 3D printed could potentially be staked for usable samples with Nano.
Yep. Thank you, Kenneth. Yeah, 1.5 millimeter works fine. That's great. And
There was something else about the 3 millimeter. That
I think Andre is asking about the OD of the tool. Oh, the OD of the tool. Yes, we'll get into the dimensions of the modules in just a minute.
Yep.
Okay. Multi-head automation. So this is on a dial, and you can see there's. Do you know how many stake points were in this? Like 20? I haven't counted them.
20.
And you can see they're all independent of each other. So if you watch closely, you'll see the LED lights change color all at their own time, because what the process is doing is every module is processed independently. So they're each waiting for them to hit that precise cooling temperature before they retract.
Yeah, those are all run independently. So they are all focusing specifically on their exact point, and those are all customizable through process for each module.
Yep.
Did have a question come in about PPS. We'll talk about materials later, I think.
We can talk about it now.
Yeah.
What kind of materials would you say are, thermoplastics are best for NanoSTAKE.
Yeah.
Are there any materials that you'd want to shy away from with NanoSTAKE?
So the ones that not necessarily shy away from, but we have to give some consideration to are sticky type materials, PCs, PCABSs, PBTs, those types of materials that like to stick to hot tools. We do have to kind of process around those. It can increase your cycle time because we have to lower the temperatures enough that we get above the VICAT softening temperature, but kind of below that melt. There's a sweet spot in those sticky materials where we can still melt process them without sticking. So there's just some care given to those. Some of the higher heat materials, again, we just have to work around processing. Somebody mentioned, I noticed in the chat, 30% glass-filled PPS. So we have done PPS in the past. We can stake them. The window, processing window is a little bit more narrow with PPS. It's a highly crystalline material and it likes to set up really quick. So as soon as you turn the heat source off, it wants to start solidifying again. So your process window is a little bit tighter with those types of materials, but they heat stake just fine with Nano. We can usually process around those.
Michael asked how the equipment controls the tip end stroke and the tolerance on the travel. So we do have there's two things. We have a linear transducer that's used to measure the position of that punch. And so we're monitoring the position and making sure it hits a programmed final height. So that final height is what we know is, okay, this is fully staked. And then there's also a lock nut that will prevent the module from over traveling. So there's there's a hard stop. So if you forgot to load a part or something like that, or you forgot to load the mating component, the hard stop is going to prevent that module from just burying itself into the lower component or into the nesting or something like that.
Yeah, because a lot variation with polymers can change how they react. And so if you're staking by both time or position, if you get a lot of material that happens to react differently, that hard stop is in there as a fail-safe.
Yep.
And with the linear potentiometer, you can set up your boss detection for starting height and finish. So it can detect for short shots, missing boss posts, as well as, hey, I didn't get to my final resting position. Something went wrong in the system, and it can flag for the short stakes as well.
Does the linear transducer compensate for variation in the part height?
So you're probably talking tolerancing. Yes, in a sense it does. that has to be built into the process, though, within the window. So if it's a little bit taller or shorter, that's based on the parameters that you would set. So you can then dial that in for a specific height, starting height and finish. So those parameters are set and controlled based on your input.
Is the plastic boss design, like wall thickness and height, critical for successful nanostaking? Yes, absolutely. So some benefits of NanoSTAKE. Why don't you talk us through these benefits?
So one of the reasons that we developed Nano was historically we had two different types of modules with infra. We had a 32 millimeter diameter and a 20 millimeter diameter. And as everybody knows, especially in automotive and some other areas, we have packaging spaces that are getting a lot smaller. So things are getting smaller. We have to stake PCBs into very tight spaces. And so that 20 millimeter diameter body was still a little bit tight to fit in places. So we developed Nano. So the diameter of the body itself is 8 millimeters in diameter. So we're talking roughly, 9 millimeters of clearance, let's say, that's needed for those tight spaces. So safe for electronics, we talked about that a little bit. We don't have to worry about desoldering or getting close to sensitive components. Low energy consumption, we're using less than 2 amps. So a very, very low energy consumption. When looking at this compared to other technologies, whether that be ultrasonics, hot or cold stake, that energy consumption is much greater. So it is a soft cost that needs to be considered when looking at other technologies. You can see by the videos, this produces a very clean stake, a very consistent stake. So perception of quality with our technologies are really paramount. They look the best in the industry. They produce a consistent, tight stake every single time. It is reliable and repeatable. The nice thing about this compared to screws, I think somebody actually mentioned screws earlier. Mm-hmm. I'll touch on that a little bit more.
Screwing everything together.
Yeah, we screw everything together. Yeah, that's one of our key initiatives is screw replacement. We're seeing a lot of customers trying to get away from screws. The tamper evidence is one of those areas. You don't know that a screw has been removed and replaced with staking technology. You do. We do have a smart release, so if you are dealing with sticky problems and need that cycle time to be able to hit it with a higher temp, we can use smart release, and what that does is it basically flashes it right at the end with a burst of heat and low pressure to try to retract that from the sticky material. You don't have to worry about Class A read through. The precise temperature control allows us to kind of drive that heat in just as much as we need it and not be able to bleed through to the Class A side. So here's our module design with our 1-to-1 air cylinder. So the one on the left is basically our core technology. That's our single module that has the LED light built into it. But then on the right is our 1-to-1 cylinder, and that's where the linear potentiometer is built into that black housing there.
Here, and I can point that out actually. I go up here, this is that black thing.
Yeah. That's the linear potentiometer inside of that.
So that's what's monitoring that position. And then if you would point out that hard stop there also on the air cylinder.
Right
there is your hard stop. So that's controlling the stroke there.
Let's get that terrible ink off the slide. Okay.
So this is what you would expect to see if you were to order an integration package or a machine from Extol.
So we often get asked, how large should my boss be? And really, the question should be asked, how strong do you need your joint to be? Because the size of your boss is going to impact how strong your part is. And so you can kind of work the other way. If you know how strong your assembly needs to be, then you can work to calculate the size that you'll need and how many stake points you need. But before we get too far down this path, you can follow along. We're not going to go through this like step by step, but the design guidelines here, let me change my cursor here, are available on our website, and you can get these. If I go, can I just click? I know you can't see that, but I'm going to paste this link into the chat to make it easy for you guys to just grab this while we're talking, and then you can have this up on your end while we're going through the presentation. Okay, so design guidelines are available, and now let's talk through it.
Yep. So strength, really, if you break it down at its simplest terms, we want to stack as much material above the cross-sectional area as we can to an extent. There is a point of diminishing return, but really you get your strength from stacking that cross-sectional area where the boss goes through that through hole. So there's a calculation that we can use, and it's based on that parent material strength of the polymer. So there's a safety factor that's typically applied. Unfortunately, there's not a static number for that safety factor, so some development work has to be done in the lab to really nail that down. With infra, it's a little more static. So with infra, we typically designate a safety factor of about 20%. It does vary because the difference between infra and nano is that the processing temperature can vary your strength drastically. So we've seen that the lower temperatures do produce stronger stakes. So it really just depends where you're processing that material and how hot you're processing. Our safety factors, just to give you a rough general idea, we're kind of seeing that more in the 50 to say 80% range. So we would apply at worst maybe 50 to 100% of that tensile strength on the parent material. So, but we can help you with that calculation. Through hole design is important as well. So the tighter that through hole interaction is, we try to keep that at about 10% of the boss diameter, going up to about as much as 25% is the most we like to see. So anywhere between 10 and 25%, as long as we're in that range, you're probably going to get the strongest joint possible. So tighter the better. We understand that's not sometimes feasible, so we have certainly staked material that has 35-40% larger diameter hole. You just sacrifice strength.
Mm-hmm.
So here's some of that math that's behind it. We won't go into that in great detail. So as far as solid round boss designs go, here's some of the best practices we like to follow. Again, that through hole being 1.1. We do like some sort of radius, whether that be convex or concave. We do like to break that edge on that boss. It does provide significantly more strength when you're talking about boss strength. So we like to see those edges broken, have some sort of radius. It doesn't necessarily have to be to that specification there on the right, but some sort of broken edge is kind of what we're looking for. Height versus diameter. We typically like to see, I think, do we have that listed here? I think 0.8.
Yeah, I mean, it's anywhere from 0.8 to like 1.5, I feel like is an okay height for the diameter.
Yep. So we do have some limitations on the 1-to-1 cylinder as far as height goes. So I would say you're probably maxed out in that 5 to 6 millimeter height range. We have done larger. We actually do offer an extended cylinder, which can get up to, I believe, about 10, 11 millimeters. Once you start getting into volumes above about 50 millimeters cubed, that's where we really want to do a lot of that work in the lab, though, to validate we can actually get a form stake correctly and that it meets your specification. So these are just kind of those general rules and guidelines. So you can see we like to kind of stay in the 2 to 4-ish diameter and somewhere in the same height. Again, this is not a hard, set, fast rule. We have done much larger. But it does take some work to refine that in, and usually your processing window gets a little bit tighter.
Michael asked a question: what is the design parameter of the staking tip to prevent and build up on a dome surface? I'm not sure exactly what you're asking. Are you trying to figure out a certain dimension, or?
I guess as far as buildup goes, we don't coat our nano tips with anything to prevent that. That's typically driven by process. So if you are getting sticking and buildup, that's usually remedied by processing. So we're either going too deep and we're curling the material up around the tip where it doesn't like to release. We like to keep all of that material in the cavity. So there's possibly some design limitations there where you might be potentially undersized in volume on the punch. The other thing is with sticky materials, like we talked about with PBTs and things like that, we could be processing too hot, and then you could be getting some sticking. And once it starts sticking, it gets much worse, much faster.
Yeah.
So we do design to about 95% of the CAD. So, kind of back to that point, if you start to get your bosses varying to the high side, you can start to overfill that cavity and it has nowhere to go but out. And so in severe cases, if you're over driving, you haven't set up your hard stop, specifically where it needs to be, and you start over driving, you certainly can get sticking, and then once it starts, it's hard to stop. Then they have to be cleaned.
Yeah.
So we do also design for rectangular boss. So we do tab styles as well. The interaction of the through hole is very similar in design for our round bosses. We do stake, tab, round hollow, round bosses, solid. So there's a couple different designs we could use. Similar in volume, though, we like to stay roughly under about 50 millimeters cubed, and we'll design that again to about 95% as well. So as far as the strength goes, again, we mentioned that through hole interaction is very important. So with the through hole being in that 10% to 25% range, you're going to get the strongest joint. If that through hole starts to get much larger, as you can see on the right, that's an exaggerated design, but
you'd be surprised at some of the things that we've seen before.
So as we design to that 35-ish percent diameter in our finished stake height versus your starting boss diameter, as you start to get larger, you could potentially get to a point where you're just hanging on to the hairy edges of that stake point. So really, we like to try and keep that tight. And in some cases, we have customers that have very little tolerancing in there, and they're almost press fit. And those provide the strongest joint. We obviously know with larger, as you get bigger parts, your positional tolerancing has to grow. So
my recommendation in that scenario, if you have a lot of variation that you need to compensate for, I feel like one of the best solutions is to design your through hole as more of a slot, so that it's more of a two-way, and that way you can get some compensation in the direction you're expecting, but then you can still have two of the sides of that hole be tight to that pin. That'll allow you to at least get some strength out of it versus a giant hole that we can barely cover with a stake head.
Yeah. So with glass fiber materials, which we run into a lot, Obviously, the shrink rate with flow versus transverse is quite different. So, to Jason's point, if you can use that to your advantage and tighten up that through hole in the flow direction because you're going to have less shrinkage. Designing around that to try to get it as tight as possible is optimal.
Yeah. But I think what we really want to communicate here is that a small through hole is ideal and it's very important for strength.
Yeah. And we will flag that in the design phase as we're doing some of that work ahead of time to try and run through feasibility.
We'll tell you your design is terrible if you have a big through hole.
So spacing, if we were to use a center punch on a 8mm module, we like to see roughly 10 millimeters center to center. That's optimal. That gives us, that 1 millimeter for each module in spacing. So in a perfect world, we like to see 10 millimeters. We also understand the world is not perfect. So to remedy that, we can offset our punch. So if you do have a boss that's, let's say 6 millimeters center to center, we can offset and position each one of those modules and flip the 1-to-1 cylinders opposite of each other so that we can stake those bosses a little bit closer. We do start to run into limitations, but 6 millimeters is not the closest we've staked. It just depends on the diameter of the finished stake head. Mm-hmm. Obviously, you can't get closer than that.
Right.
So based on that, I would say we can probably get as close as the finished diameter of your boss plus 2 millimeters. So if you have a very small boss head, you should be able to get a little closer than 6, but we can help with that design. As far as angles go, we like to have a flat surface to come down on. So if you do have an angled primary surface, we like to have that secondary surface either stepped, like the center grate design. What we don't like to see is the one on the right labeled poor design. So in this case, the only way we would be able to get around that is by angling the boss cut into the punch. And so it starts to create problems with, it wants to kick out and slide. You'll start
like it's a little ramp that they're going to go down.
Yeah. You'll start to see some shifting where that final head is related to the center of that boss. So you'll start to get some shifting, very inconsistent results as far as strength goes. So if at all possible, try to design to the left 2 and not the right. So one of the unique methods that we can employ with these types of scenarios that you can see on the screen here, a lot of technologies we can't really do with like infra, let's say, these severe angles. You'll start to get drooping a little bit where we're heating up the material before we've driven the punch. So a scenario like this would not be great for some technologies, but for nano, it works. The caveat to that is, again, the one on the right.
Don't do this.
Please do not do this if at all possible. But it just shows we can really stake in any angle. We can come at it from the bottom, the top, a 45 degree. It doesn't really matter. Gravity doesn't necessarily play a huge role when it comes to nanostaking. So finished stake shapes. We have a couple different punch styles that we like to use. For traditional round, we usually use a puck style or a more traditional stake, which I think we've got. Yep, there we go. So we've got the puck style that's shaped obviously more like a hockey puck. We have our traditional dome. That's typically what we use in infra. We have found that the puck style with NanoSTAKE does result in a stronger staking joint. So most of our NanoSTAKE designs, we typically use puck. We can use dome. In some cases, they do perform a little bit better. Rosette would be used on a hollow boss, and we typically use this when there's low volume that we need to push out to capture that 35%. So if you've got a very small hollow boss, what we would do is use a rosette to kind of gain some surface area. So we can use a rosette to do that. And then our standard dome shape for a tab is that elongated dome.
Do we know, like, do we have any percentage? Ken's asking if there's a certain percentage stronger if we use the puck versus a dome.
So it does have some relationship to material. So I would say roughly we've probably seen somewhere in the neighborhood of 10-15% stronger is what we're looking at as far as a puck goes.
Last app we used all dome and we got something like 30 newtons ish.
Yeah. And if you switch those all to puck, you may see a slight increase, let's say 10%. Where we have seen most of our value in increasing strength has been from the processing side. So NanoSTAKE is relatively new, 7-ish years?
Yeah, 7.
So we're still learning. And over the last few years, I would say we've started to learn a lot more about the effect of processing temp. And so the biggest bang for your buck, if you need to increase strength, is typically staking at those lower temperatures. So we've seen some correlation across the board, no matter what the material, based on that.
It's important to know that we're designing each NanoSTAKE punch specifically for the boss it's staking. And so this kind of shows just some examples. These are 3 different punches that we've used in different applications. And you can kind of see how, like, there's just very unique things that we can do to try to meet the requirements of whatever the space you're trying to fit your NanoSTAKE punch into.
So you can see the one on the right is kind of what we showed earlier. That offset punch allows us to get center to center spacing a little bit tighter. That one in the center is I believe, the hearing aid application where the boss was very, very tiny. And then the one on the left, that one is an extended punch. And so this is where we probably had to get down into a pocket or a blind hole potentially. And so typically if there were no restrictions as far as a blind hole or anything like that, we would build that punch right at the tip. So the closer we can get to the module heater, the better. But in this case, we probably had to get down into, like I said, a blind hole, so we can extend those up to a certain degree.
So Paul is asking about sealing applications, and then Jason says, similar question, do you have experience with staking airtight hermetic seals for pressurized applications? So are you talking about potentially like an application where there's a hollow boss, and by staking that boss closed, you've now hermetically sealed your part? Because I know we've done it for InfraStake. Have we done it for Nano before?
Typically when you talk true hermetic seal, that excludes staking altogether. But
if you had a hollow boss and you were just simply staking that boss closed, that could be, as long as everything else in the part is closed off, that could be a hermetic seal.
Could be.
Yeah.
Yeah.
And so I don't know that we've done that in any specific applications for NanoSTAKE. We have done it for InfraStake. There was some really unique application where they had these balls that had water in them, like halfway filled with water, and then there was a little tiny hollow post. We staked it shut, and then they used them in like lakes or reservoirs to like keep birds off of them or something like that. They'd like put thousands and thousands of these balls into the reservoir. So that was a application where we did that with InfraStake. I don't really see a reason we couldn't do the same thing with NanoSTAKE, but it would be your boss size would be limited to a smaller boss.
And as long as the two materials were similar, I would say we could probably overdrive it, drive into the base material and provide a seal.
Yep.
But that would be something we would definitely want to trial in the lab.
The other thing that you can, what we've seen people do, if you're bringing two components together and you're, staking it down, that's not a hermetic seal. But if you have a gasket between the two, then you can create a hermetic seal that way. And that's what you see a lot with, things that are screwed together. Often, if a hermetic seal is required, you put a gasket between the two. And the same would work for staking.
Yeah. I did, before we got any further, I did want to touch real quick on screws, because I did see a couple of those come up in the comments. So if you do have a screw application, we'd love to look at it, because we are using Nano and Infra to replace screws across the board with a lot of our customers, and we're seeing a lot of great success. I know screws, it's an extra SKU that you have to manage, torque out issues on smaller screws. I know the cost of plastic biting screws have gone up significantly, and if you can integrate that in, it's pretty much a low to no cost solution to switch over then to NanoSTAKE or InfraSTAKE. There is that capital that needs to be invested up front, but then after that, you get the cost savings. So for serviceability, we do have some designs. This doesn't have to be a one and done. So we do have some designs we can help you with, where you would stake it initially. If you have to service it, you would chop or take off those punch heads. And then you would just drive the screws as you normally would into that hollow boss. So anyway, serviceability, I know, is always a concern, or has been a concern with staking, because everybody thought it was a one and done. That's not the case now. So please bring those applications to us, and we'd be glad to help.
Do we have experience with vibration testing validation when replacing screws with NanoSTAKE?
Yes. So we have done this. In particular, we have done this a lot with forward lighting type applications, where in automotive, vibration is one area that they always test for. So we do have a lot of information based on that. That's one thing that's really hard to understand from a design. So it's hard you can't FEA that. You can't design that into a software that you can say, yes, it will pass vibration. What I can say is that it works today, and we typically just have to add a few extra points, which again, if you're molding them in, it usually isn't an issue.
Yeah. Which heat stake equipment generates the least heat around the staked boss? So here's our staking technology slide. Which one creates the least amount of heat around the staked boss?
I would say
InfraSTAKE
is probably the safest for sensitive components. I would say Nano is the next. And they're probably pretty close, but Infra, we're driving that energy radially. And so you can see in the slide here, we're directing traffic, so to speak, around that boss radially. And we're doing that very precisely. Yep. We're not getting much leak into the green area. We actually do a demo sometimes where customers just don't believe that, because it's getting hot enough to melt plastic. How does it not drive energy into that secondary source? And we'll demo our demo kit where we actually pinch a piece of toilet paper in between the module and that green material. And not only does it not ignite, you see no witness mark of any kind of burning or charring. So that one in particular, I would say, is probably the safest.
Yep.
Nano, we are able to control that temperature very precisely. So we can typically, in most materials, get, like I said, above the VICAT softening temperature, which in most cases is fairly low, to where we're actually able to melt and move those molecules to a point where we're not burning anything else.
Yeah. I mean, even if you look again at this thermal video, you can see right where the temperature, there it is. there's like nothing on you can't even see the washer in that thermal video because it's not getting hot.
Right. Yeah.
Is there a way to increase the cycle time? I mean, if I have a shorter machine cycle time, the tip needs time to reach the temp. Is there a way to set different power levels for the tips?
Yes.
So the tip goes from ambient temperature to operating temperature, whatever that is, whether it's 500 degrees Fahrenheit, 600 degrees, in like seconds. Now, in fact, in this video, the tip starts out of frame above the shot, and then by the time it's in frame getting to the plastic part, it's like almost all the way to temperature already. So, and then we cool it back down to ambient temperature every single cycle. So it's like a second or two to cycle temperature on these things. As far as different power levels, we don't have to do power levels because we can control the temperature of the tip precisely. So we can set the temperature to whatever we want, 200 degrees, 300 degrees, 325. Like we can precisely control the temperature of the tip.
Up to about, what, 750, 800?
Yeah. Yep. How does the rapid heating and cooling affect the tool life?
Yeah, it's we've done a lot of studies and have a lot of knowledge now based on the fact we've been producing these for, like we said, about 7 years. And really the heating and cooling is typically not the weakest link. We did early on make a change to the pogo pins inside the module, which now we're seeing much longer cycles on these. So there are some contact points within the module that touch off on the heater core. Those were gold plated. We've made an internal running change now to those. And so, we have hundreds of thousands of cycles being ran on these at customers, sometimes millions. So I would say, it depends again on environment. So there are some sensitive components within here, so we don't want to be bouncing these around real heavy, moving platens back and forth at breakneck speed.
Yeah.
But I would say if you're gentle on them, just worrying about rapid heat, rapid cool is not the weakest link.
Yep. Does the tip need to be at the plastic melting temp or just the glass temp?
It needs to be north of the glass transition temperature. Usually, well, it depends on the material, whether you're talking about a semi-crystalline or an amorphous material. I would say you're probably looking at somewhere near the glass transition temperature, north of the Vicat softening temperature to get it to move. Basically, you're just trying to get those molecules to be excited enough to mold. You're talking about the difference between like a candle. We like to use the analogy of candle. So if you warm up a candle north of its solid state, you can get it to a point where you can manipulate it almost like clay. You get it hot, even hotter than that, it will turn liquid. Most materials have that same transition phase. So we're trying to get it to a point where we can manipulate the plastic, but nowhere near melt.
Yeah. What would you say? What would you recommend temperature-wise for PC?
PC is probably, I would guess that PC or PC ABS blends, depending on what your cycle time requirement is. Again, that's the balancing act. I would say you're going to be anywhere between 450 and 550.
Yep. Gerardo, yes, we do all NanoSTAKEs all at the same time, all simultaneously. So 6 stakes would not be a problem at all. How do you get NanoSTAKE for your project? So we build turnkey machines here at Extol, like the one you saw in the video. That's actually a screenshot of that video, that machine where it was a dial machine. We've built machines where it's more standalone, and the operator's loading up one part, staking it, and then taking the parts out. And then we also sell integration packages. So if you want to build your own machine or you have a machine builder that you are comfortable and used to working with, they can get the integration package components that they need to make NanoSTAKE work inside of that machine. So if you're interested in getting NanoSTAKE or at least exploring that, I'd encourage you to just simply in the chat here, you can just say, I want NanoSTAKE, and we'll follow up with you. Or you can go onto our website and submit a quote request. What will happen is we'll schedule a discovery call and learn more about your project. We want to work with you and figure out, is NanoSTAKE a good fit for you or not? So we'll review your design. We'll stake some test parts if you have them. We'll offer recommendations. And then from there, we'll decide if the NanoSTAKE is the right thing for you and what would the best equipment solution be. So feel free. You can say, I want NanoSTAKE right there in the chat, or go onto our website and submit a quote request. Great, Gerardo. We'll make sure to follow up with you. While we still have a few people left on the call here, I want to advertise for our next webinar, which is only 2 weeks away. We'll be talking about InfraStake. So this was all about NanoSTAKE and how to design for NanoSTAKE. In a couple weeks, we'll talk about how to design for InfraStake, and that'll be on Tuesday, July 29, 11 a.m., just like you always, and it'll be interactive just like this one was. We appreciate all of you guys for joining and asking lots of questions throughout. We'll stay on for maybe another minute or so while you guys ask if you have any other final burning questions. Otherwise, I will be sending out the recording of this webinar later today at some point once I've had a chance to process the whole thing. And hopefully you guys got what you wanted out of this. Is there anything that you were hoping to learn that we didn't cover yet?
Well, the other thing, while we have roughly 36 people, we are actually spitballing the idea of having a on-site training, so to speak, with InfraStake and NanoSTAKE, where we wanted it to be a little more interactive. So you would actually bring parts, obviously items that are not in development. We won't be signing NDAs and things like that. But if you have something in production, you just want to see how InfraStake and NanoSTAKE work, we would have our lab set up so that we could actually stake your parts. Yeah. So if you're like, I only do ultrasonics, I would love to see what kind of strength we get with InfraStake versus our ultrasonics. We could actually be doing some of that staking in our lab with your particular part. So anyways, we'll send out some communications here, kind of getting a rough idea of the interest. But
would you guys be interested in kind of like a staking workshop? We're in Zeeland, Michigan, so you'd have to come here, and we would do kind of we'd train you and then be able to go into our lab and stake your parts. Like, you bring samples and we'll put them on a robot and test them. It sounds like some people are interested in it, so that's good. Yeah. Cool. Well, with that, we will wrap this thing up. I hope you all have a great rest of your day. Thanks again for joining, and we'll see you next time.
Thank you, everybody.